With that, I'd like to introduce our keynote speaker, Pavan Balaji from Meta. Dr. Balaji is a research scientist and a technical lead at Meta Programs. In his current role, he drives early industry partnerships for developing large-scale supercomputers in support of the Meta's AI workloads and the design and optimization of HPC networks and communication libraries and their supporting ecosystems. He's a senior member of the IEEE and a distinguished member of the ACM. Pavan?
Thank you, Bill. All right, so let me try to share my slide deck. All right, can you folks see my slides?
Mm-hmm.
Yep, great. Take it away.
Oops, sorry, one second. Technically challenged here. Can you still see it?
Perfect.
Okay, great. Well, thank you for the introduction, Phil. I appreciate it, and I would like to also thank Raghu and the organizers of this workshop to invite me to give this talk. I have attended this workshop a few times in the past, but I believe this is the first time I'm giving a talk, so I'm very excited about that. I was when I was asked to give this presentation, I was originally wanted to talk about just the network and comms challenges at Meta. But while I was thinking through it, I felt that most of the challenges are very context dependent. We need to understand what we are trying to solve, why we are trying to solve it, what our constraints are, to understand what those challenges are. So I decided to change the theme a little bit and focus solely on Llama 3, which is the new buzz recently, and explain the context behind that, explain how we built out the infrastructure needed for Llama 3, how we are for our training and serving infrastructure, and what challenges we ran into in doing that, and how we tackle those challenges. Hope you find that useful. I was planning to start with a video of some of our leadership talking about our infrastructure, but I think we are having some difficulties with sharing the audio. I set up one more thing. I'm going to give it a shot. If it doesn't work, someone should call it out. I'll just stop the video and move on. Let's see if this will work.
Nope, no audio.
Can you hear anything? No audio? Okay, never mind then. Sorry about that. It's one of those, cheesy videos, cheesy no content videos, which just talk about how awesome everything is. So you're not really missing much. It is available on YouTube if you'd like to take a look at it. Anyway, let me get to the deets of the talk itself. AI at Meta is pretty heavily used. It's used in a lot of places. Many of our products are powered by AI with no human interaction in the backend. I will talk about there are many products, many different models that are AI powered at Meta. If you squint enough, you can kind of separate this out into two broad categories. The first category is what we call recommendation and ranking systems. These are essentially systems that make personalized recommendations to you by looking at your previous interactions and predict what might be of interest to you in the future. This is our core engine that powers many of our products. For example, when you go on Facebook feed or Instagram feed, the things that it recommends to you is all powered by this. Our ads business, for example, is powered by this. Search is powered by this, and so on. It's one of the very core pieces within Meta. It uses, internally, it uses what we call deep learning recommendation models. It's a broad category. We have many such models. These are extremely large, very sparse models that we use. This is still the bread and butter at Meta. It powers a lot of our engines. I won't focus a lot on these sort of models in this particular talk, but it is a very important and very interesting model class of models for us. There's a link at the bottom over there. It has an example recommendation model called DLRM, which you can download and try it out if you're interested. The second broad class of models are what we typically call content understanding and content generation models. Generative AI or GenAI is of course one example of such models. Llama series family of models were announced over the last couple of years. Llama 3 was recently released with 8 billion and 70 billion parameters. We have a larger version coming out soon with 405 billion parameters. This is, to our knowledge, the largest dense model that is available in the market that is used in production. There are some other models that have been used for like benchmarking and papers and so on, but not in production usage. So this is one of the largest dense models that we are aware of, and it performs quite well. Now that's just the model in the backend. Meta AI is our user visual product that is internally powered by Llama 3. This was announced, I think, last year, and many more products are, of course, going to pop up, but that's one of our first products that internally uses Llama 3. Okay, let's look at where we are with respect to our capabilities with respect to generative AI or Llama in particular. We only started working on this about a couple of years ago, around mid 2022. And when we started, the model worked, but it was it's still primitive in many aspects. So the picture on the left, there's a prompt on the top that you can see. If to imagine a picture of a pug in a superhero outfit and so on. By the end of 2022, around December 2022, we still could generate it, but it was more cartoonish in some ways. Within 6 months, by the time we got to Llama 2, by June 2023, we were at a spot where we could generate much more realistic, much more intricate pictures, which were very realistic looking pictures with a lot of bright colors, a lot of details associated with that, and so that you can see on the right hand side. This is a previous generation of Llama family series, Llama 2. That was last year, that was mid of last year. By the time we got to Llama 3, this year's models, the focus was a lot on improving accuracy through larger models, more and high quality data, and ability to ingest more context. And Llama 3, there's some pictures over here, integrations with Instagram, WhatsApp, and Facebook Messenger that showcase how Llama 3 is used by the end user. Now, that's just the user visibility part of it. Of course, in the back end, it's the infrastructure that's supporting all of this. And speed and accuracy, these two are the most critical aspects from a user experience perspective. The challenge over here is to achieve both of them. Accuracy requires large models that are trained with a lot of data and can take a lot of context. Speed is how quickly we can respond to these queries. And the larger the model and larger the context and so on, you get great accuracy by doing that, but you lose speed in doing so. So achieving both of these together, these are like strong duels. It's very hard to get. If you get one, you're usually trading off or losing out on the other. So the challenge over here really is to achieve both of them at the same time, and that's where most of the work on the infrastructure comes in. We want both large models for high accuracy, but we also want to be able to respond to queries quickly with respect to speed. All right, that's just a background of how our user visible products look like. So let's look at the infrastructure that is powering these sort of models. So Meta's GPU computing infrastructure is very large. First of all, Meta's infrastructure itself is very large. It spans dozens of data centers across the world. And AI, of course, is a significant part of our compute infrastructure. In fact, most of our compute infrastructure is used to power AI models. This is powered by multiple types of GPUs as well as our internal silicon that we announced, I think, last year or early last year, I believe, called TIA. These models are powered by both of these combinations of GPUs and internal silicon. And we have a lot of these. Just our NVIDIA H100 GPU portfolio is expected to reach about 350,000 GPUs by the end of 2024. That's just the H100s. That doesn't include other GPUs like A100s, even V100s, or GPUs from other vendors or our internal silicon and so on. If you include all of these together, our portfolio is almost equal to almost double that of this number that is presented over here. Around 600,000 H100 equivalents is where our entire portfolio is. So it's a very large infrastructure. A lot of that is, it spreads across many different areas. Of course, some of that is used to power llamas. Some of that is to power our recommendation models. Some of that is for training. Some of that is for serving inference and so on. So it's a kind of a combined portfolio across all of these areas. Let's talk a little bit about the system architecture itself. I was hoping to put up a picture over here of how some pretty pictures of how the system architecture looks like, but I couldn't get the approval in time, so I'm going to use text to describe some of it and drop a few cartoons. Here's roughly how it looks like. In end of 2022, we had released our system architecture in OCP Summit, what we called Grand Teton. That's our architecture for a large part of our internal infrastructure, including the infrastructure that supports Llama 3. So it's a full supercomputer. It is comprised of many racks. Each rack has many nodes or chassis. Each chassis has multiple CPUs. It has 8 H100 GPUs, NVLink switches, PCIe switches, and there is one 400 gig RDMA network adapter per GPU. So you have 8 GPUs and 8 RDMA networks per GPU. So within that box, a bunch of front-end network adapters as well for TCP/IP traffic and so on. So that's each chassis. So each chassis has 8 GPUs and 8 RDMA NICs inside that, and NVLink as well. And you have 2 of these chassis inside a rack, and a rack level switch, a single crossbar rack level switch within the rack. Now you have many of these racks connected together with a layer of core switches. So that's a second level of switches, and you have full bisection bandwidth between these sets of racks. Some number of racks are connected together with a core switches to get full bisection bandwidth. This set is sometimes internally we refer to it as an AI zone. It's a full bisection bandwidth collection of racks. Now these zones themselves are connected with what we call aggregation switches. Multiple of them they are connected together, but these are tapered, so we don't have full bisection bandwidth between these sets of zones. So I have a picture over here. Maybe I should have shown this first. I don't know if you can see my mouse, the cursor over here. We have 16 GPUs per rack. We have a rack switch. These rack switches are connected to core or cluster switches. So this is the second level switches. So this part is called an AI zone, a full bisection bandwidth zone. And then multiple of these are connected to the third level T-buffer switch, which is tapered at some level of some granularity. This is our Grand Teton GPU architecture. Now, we use this for both our training and inference or serving platforms. Serving, we use lesser network capability, but training, we use more network capability. I think most of you over here know how training and serving works, but a quick 101. We take a untrained neural network, we train it with some data. Essentially, it ends up with a set of weights for that neural network. So if you think of the neural network as a math equation, it comes up with the coefficients for those math equation, and we have a trained model which is fully capable, as in it has the already trained set of weights or coefficients that have been computed. During inference or serving, we take this trained model, we feed it new data, and get it to predict what the output should be. Now, this is a simplification. It talks mostly about classification models or content understanding models. Generative AI doesn't exactly work this way. It is more of a content generation model, but it kind of gives you an idea of how these training and serving systems work together. Okay. All right, let's get back to Llama 3. Let me see how am I doing time, 20 minutes in, okay. Let's look at training Llama 3. Now, Llama 3 training was supported by it was supported on many supercomputers, of course, but that included two large medium-scale supercomputers, each with about 24K H100 GPUs, about 50 exaflops of peak FP8 performance. Both supercomputers are based on the Grand Teton architecture. One supercomputer was based on Rocky, the other based on InfiniBand. There are some details at the links below if you're looking for more information on this. These two supercomputers were almost identical to each other, except one was Rocky based, one was InfiniBand based. There are some additional differences, like the picture that I showed a few slides ago was the Rocky-based architecture. The InfiniBand-based system was similar, but it was using more like a rail-based topology rather than a full class topology. But at least for the first order of approximation, they are very similar to each other. So each of them was about 50 exaflop performance, and we used two of these plus a bunch of additional smaller supercomputers to train the various models in Llama 3. Including the pre-training, fine-tuning, and of course, surveying. With respect to the data and storage, of course, as you know, many of you are aware, high quality and high volume data is essentially the backbone of deep learning. Llama 3 is no different. It was trained with 15 trillion tokens of data, which is much larger than Llama 2. So this is a lot of data that it's trained with, and we do need fast access to this data to the training. Our storage infrastructure was heavily based on Flash for speed purposes, for performance purposes. This included the raw data itself, where we would keep the data to process it, but also generated like checkpoints, for example, would also be would use the storage. So this allows us to run the supercomputer with maximal efficiency without being slowed down with sort of the file IO itself. That's for the main, the core IO, if you will. We also co-developed an NFS solution with Hammerspace to allow for more, let's say, user-friendly IO access, like interactive debugging is an example of that. So we have this dual sort of IO solutions for our training system. All right, so before I move on from the Llama 3 training itself, I want to tell a little bit about our recommendation models too. Now, a lot of the talk that I was giving, in the infrastructure I was building, was for Llama 3 or generative AI more broadly. But I do want to remind that training recommendation models or ranking models, that is still a large part of our infrastructure. That is still our bread and butter, so we can't just leave it. So we have to build our infrastructure, even though we are using it for Llama training, we want to make sure that it is useful and can be used for our recommendation model training as well. I won't spend a lot of time on recommendation models, but I want to give a little bit of a feel of how these models look like. The recommendation models are special. They're not like your Llama or GPT style models. The traditional Llama GPT style models are very dense parameter heavy, which means that you have this model, or smaller content understanding models. They have these dense parameters, and you replicate the model across a bunch of servers, a bunch of GPUs, and split the data across these GPUs for training. As these models are training, you're essentially only synchronizing the gradients or diffs, if you will, between the GPUs. So the amount of communication you're having is not that significant in traditional dense parameter content understanding models. The recommendation models, on the other hand, are a little different. They are together, they also have dense parameters, but together with that, you have a lot of sparse features, sparse parameters. What this means, in fact, we have like each of these features are presented as tables, and you have hundreds of tables. Each table has hundreds of millions of vectors. So you're talking about tens of terabytes of, tens of trillions of parameters, tens of terabytes of data. And you can't fit these models into a single GPU. So you have to essentially spread these models, divide up these models across hundreds of GPUs, and you have to do very heavy communication between them to be able to synchronize these models. So the artifact of this is you have, well, first of all, you have very low compute utilization because you're doing very small gems, you're doing a lot of element-wise operations. You have a lot of irregular memory access because when you're accessing sparse features, you're not doing this memcopy style like contiguous access of large data. You're reading bits and pieces of memory all over the place, random access of memory. So as you're aware, that creates a lot of performance issues. And of course, it creates a huge amount of network communication traffic between the GPUs. In fact, that's one of the biggest reasons why these models cannot scale beyond a few hundred GPUs, because they stress the network so heavily that scaling up from 1,000 GPUs to 2,000 GPUs means the performance loss can be very significant at that scale. But anyway, this is a big class of models for us, and is something we need to keep in mind even while we are building the infrastructure for Llama sort of models. Okay, that's a little bit of background about our infrastructure itself. I want to spend the next few slides talking about some of the key challenges that we were facing with our training and serving systems. Let's start with training. So for training for Llama, we use very well 24,000, tens of thousands of GPUs. So this is mostly strong scaling to fit the model just from a GPU memory capacity perspective. We don't need that many GPUs. Maybe we need 512 or 1,000 GPUs at most. The models are not that large. You can fit it in 512 or 1,000 GPUs. Really, we are using more GPUs. We are strong scaling beyond that up to 24,000 GPUs because we really want to optimize our training time. Or put another way, for a given amount of training time, we want to we want to train as much data as we can. Okay, so strong scaling is a big aspect of these systems. Second thing is that our batch sizes are still small, somewhat small, so global batch sizes and the local batch sizes. So we cannot, after a certain point, we only like 2,000 local batch size. After a certain point, we run out of samples per GPU. So we cannot just keep scaling from the data paddle dimension for a very large cluster. So we're looking at, or we have used multi-dimensional parallelism, data and model parallelism for these sort of models to be able to scale to these 24,000 GPU systems. We use 3D parallelisms to scale to very large clusters, data parallel, of course. So if you look at the number of GPUs, the picture on the right-hand side, over here, we can divide up the GPUs. I don't know how many is this, 4, 16, 32 GPUs. You can divide it up into three dimensions. And this is a toy picture, of course, which says that each of the dimensions, you do one form of parallelism. So you do data parallel across one dimension, the Z dimension in this case, and they do tensor and pipeline parallelisms across the other dimensions. In the data parallel, of course, you're replicated the model and you're trying to split the batch size across the models. You have pipeline parallelism where you're splitting the layers of the model, tensor parallelism where you're splitting individual tensors across GPUs. Now, this is a mechanism for us to be able to scale to very large clusters so that we can use the compute of all of these clusters. The problem is that in this sort of format, it creates many complex communication patterns for the network to be able to handle. So one simple example is that now when I'm doing collectives, let's say I'm doing a collective on the data parallel dimension. So my collective itself is only across 2 GPUs in this toy example, but have 16 such collectives happening in parallel. And each collective is no longer a global collective, right? Each collective is on a smaller communicator. It's on a smaller group of 2 processes. So it doesn't have the full picture of all the other 16 collectives that are going on. And yet the communication library is expected to optimize it in a global scale because the network is a shared network. So this creates a sort of complex problems that we kind of have to figure out how to solve. Now, this is not specific to AI. This happens in scientific computing as well. Like FFT, 3D FFT is an example of that. It's a very similar communication pattern that we see in scientific computing as well. So it's not a new problem per se, but it's something we need to solve at this scale for our AI systems. Okay, before I move on from this, I want to talk a little bit about the scale of these systems. The data parallel domain is between the 256 and 512 GPUs, and it's small. It's about tens of megabytes of data. Maybe each send is about a megabyte of data. The model parallel domain is smaller. It is only like 8 to 32 GPUs, but it moves a lot of data, hundreds of megabytes of data. And you can kind of tell from the sizes, the number of endpoints and the message sizes are kind of related to each other. Because you're transferring so much data, you don't want to do it in a very large scale. You don't want to be transferring hundreds of megabytes of data or 1,000 or 2,000 processes. You want to limit the number of processes that you are dividing this across. All right. So one of the key constraints that we have to work with is we can't just go and optimize raw performance. That's almost never the problem for us. It's really, that's not our key bottleneck. Like most hyperscalers, one of our key bottlenecks is power. That's really what we are bound by. And we can't just go and purchase more power. It doesn't work that way. Every company has some commitments, environmental commitments. Like, for example, Meta is committed to sustainable data centers for 100% renewable energy. So any amount of power that we take from the power grid for running our data centers has to be refilled in some sense by using solar or wind farms on the same power grid. So you can see a map on the right-hand side over here. Every place there's a data center, there are a bunch of solar or wind farms to try to feed that power back in into the same power grid. So essentially what this means is that we have power is our basic resource, and it is a growing resource, but it's a very slowly growing resource, which means a lot of the system, a lot of the infrastructure that we develop is not directly optimized for raw performance, but rather it's optimized for perf per watt. How much performance can I get out of a fixed power budget? So many design choices that we make are based on this constraint. An example is that between optics and copper, one of them is much more expensive than the other, but it's more power efficient. So we tend to pick that because our primary bottleneck over here is power. Similarly, we buy more GPUs, but run them at lower power because as an aggregate, we can get better performance for the same aggregate power usage. This, of course, assumes that our network is very powerful, and we have to put in a lot of effort to make sure that happens. But our primary research we are optimizing around is power over here. And finally, of course, Meta's internal silicon is something we are developing for much more aggressive perf per watt optimizations than vendor silicon. Okay, performance at scale. I'll give a couple of examples over here about what kind of constraints we look at from a performance at scale perspective. So first, there's a recommended reading I listed out over here. This is one of a very old paper. I think it was almost maybe 15 years ago or more. It was called Multi-Stage Networks Are Not Crossbars. It's a recommended reading. I would encourage all of you to look at it. Essentially, it says that talks about what kind of problems we would face in multi-stage networks that we would not see in crossbars. I'm sure all of you are well aware of this, but just as a quick 101, crossbars means that if I have n processes and I create n by 2 pairs of processes, these pairs of processes can communicate in any random path, and that would be fully non-blocking. That's what a crossbar is. On a multi-stage network, if I again create n by 2 pairs of processes, if these pairs of processes are communicating, there exists a set of paths where they are all non-blocking, but not all paths are non-blocking. That's a very important distinction over here. Now, unless my collective has global knowledge about every other flow that is going on in the system, it's very hard for me to find the optimal set of paths where everything is non-blocking. I can do that for a global collective, but when I have a system where I have multiple simultaneous collectives happening at the same time, it is very hard for me to go and say that, hey, this collective should go this path because I know some other collective is going to take some other path. That becomes a very fundamental problem. Right-hand side shows an example of algorithm types. Let's pick a collective like an all-gather, for example. There are many different algorithms we can come up with for all-gather. And if you look at any API implementation, you will see there are like 15 algorithms that are available for all-gather. You can have a linear ring-like algorithm for all-gather, which stresses the bisection bandwidth of the system, does not stress the bisection bandwidth of the system, but adds a lot of steps. So in fact, it requires P steps if I have P number of processes to complete the all-gather. Then you have logarithmic algorithms like recursive doubling or Brooks or whatever else you can come up with, or tree. And then you have a full mesh all-to-all sort of algorithms where I can directly communicate with any process. Now, if I have a system which has full bisection bandwidth, one would look at this and say, why would I pick anything lesser than a full mesh? Full mesh is moving the same amount of data, and it's doing it in one step. So why would I pick anything? Why would I pick a ring, or why would I pick a tree or a Brooks algorithm or anything, a tree or recursive doubling or anything of that sort? But as it turns out, full mesh is not ideal in all cases. In fact, in many cases, it's not ideal because it stresses the bisection bandwidth so much and creates a lot of contention on the system, which in practice gives bad performance. I'll show an example in a second, but one thing to remember in that in production, networks are rarely well behaved. Oftentimes, systems go up, systems go down. The scheduler is scheduling you on a random set of racks. You never get this perfectly symmetric allocation of nodes. You get nodes all over the place. And if your algorithm or your network is not able to handle this non-perfectly symmetrical allocation well, then in production, it becomes a big performance issue. Here's an example with static routing. So I mentioned this at the start of this talk. We have two servers in a rack. We have a rack switch. And there's multiple racks over here, and they all connect to a core switch. Now, in theory, this entire system has full bisection bandwidth, but it's based on a multi-stage network. Now, imagine a case where, on the ideal case, if I have a job that requires 4 servers, 32 GPUs, I will pick server 1, server 2, server 3, server 4. Right? It's a great symmetric allocation, and there will be a great balancing of my traffic. But imagine a case where server 4 is down. There's a fault, the scheduler had to discard it for some reason. So now my job is scheduled over server 1, server 2, 3, and 5. Now in this case, if I have a destination-based routing over here, I would end up with using only the first half of my core switches and not routing any traffic over the second half of my core switches. This would cause egress congestion on the core switches and loss of performance. Essentially, I'm using the same egress port for both server 3 as well as for server 5, causing flow contention and network congestion. This is what happens if you don't have a perfect allocation. Now, the obvious question is, why not use adaptive routing, right? We've been working on adaptive routing for years now. Why choose static routing? Many networks already provide adaptive routing capabilities. Well, it's not as easy when we are trying to optimize for power. When we are power constrained, we typically spread out our GPUs over large distances. That could be across, of course, across racks, across rows, across zones, across even data centers. We're spreading out our GPUs. And these distances are very large. This one is a picture of one of Meta's data centers in Arizona. Now, this is just one data center, right? It is spread out over a very large distance. And now imagine you're connecting a bunch of these data centers together. That's a lot of physical distance, a lot of fiber that is laid out. And now the communication, that's nothing we can do to improve that performance. That's basically bound by speed of light. So it's going to be a large latency over there. There's nothing we can do about it. This makes adaptive routing very challenging. Like, for example, if I have a network, high bandwidth network with a long latency, I might end up with a window of a lot of out of order packets. It's because it's an artifact of the network bandwidth delay product. So the network has to maintain a lot of state to be able to handle so many out of order packets. That's not easy for most network adapters to handle. Or we can build custom transport, non-RoCE, non-InfiniBand custom transports, because if you think about it, for our training models, we actually don't need in-order packets, right? All we are doing is a bunch of collective operations. We don't need in-order packets. We can handle out-of-order packets, but these are mostly restrictions brought about by RoCE, inherited from the InfiniBand standard, as well as from IB Verbs API. So if we build a more custom transport and a more flexible software than IB Verbs, for example, in Fabric, then we have a mechanism to be able to work around these sort of issues, routing issues better. Okay, let me switch gears over here. I've been talking about how we build the infrastructure to train Llama 3. Let me switch gears over here. Let me talk a little bit about serving the inference side of Llama 3. Now, inference is, of course, an important problem. That's what the user, in fact, sees directly. So we ask that. The general idea, I think many of you are aware, basically the ChatGPT style example using Llama 3. You ask a question, it provides an answer, then you can ask follow-up questions. It uses the context from the previous question and previous answers to answer your follow-up questions better. So there are two parts to this. When you ask a question, there is something called as time to first token. This is when is the first word returned to you. Typically, it's about a second or less than a second. Then there is time per incremental tokens. What is after the first word is returned, what is the time taken to return the second word and third word and so on. That's usually much smaller than the time to first token. Now, just within serving, these two are very different problems. The first problem is the first token is very compute intensive and very network bandwidth intensive because it moves a lot of data between the GPUs that are serving. The second problem, the time to incremental token, is memory bandwidth intensive, but it's network latency sensitive. It's not network bandwidth intensive. So low latency networks are very important for that. So here's a pictorial representation of it. When you do the first token, we use something called as a prefill. We build a transformer, we go to a transformer model and build a KV cache, which takes the input context, so your questions, the answers, and so on, the history, as well as your current question into as an input, and builds a cache, what we call a KV cache. Then after the first token, after the KV cache has been built, so this takes a lot of time. The left-hand side takes a lot of time. That's the reason why our first token takes less than a second. Now, second is a granularity we talk about for the first token. After that, once the KV cache is built, we go through that and go through this, keep outputting tokens from that. Now, this is the decode process. The decode process is typically very small message sensitive, latency sensitive, and memory bandwidth sensitive. But this is typically iterates much faster in the tens of milliseconds of granularity rather than the second granularity. Now, low latency collectives for serving are not easy to come by. Here is an example. Admittedly, this example is very nickel specific, but I want to make a point over here, then I'll draw some parallels with other communication libraries. So the way communication works in nickel is that, first of all, it's a bunch of copies over here, which shouldn't exist, but for very small messages, it doesn't really matter so much. So there's a GPU kernel. We have a GPU buffer that is sitting. The GPU kernel is copying it into a temporary buffer. Then the GPU itself cannot tell the network adapter that to transfer the data. So it tells a CPU proxy thread. The CPU proxy thread goes and issues a network IB verbs operation, which sends the data to the network. Now, there are a couple of messages over here. There's a rendezvous style clear to send data transfer message. And then on the receive side, the data, of course, we use GPU direct RDMA. So the data itself is placed into the nickel temporary buffer of the GPU, but the notification, the completion queue event goes to the CPU proxy thread, which then has to come back and tell the GPU kernel that the data is available and so on. So a lot of handshakes over here that are happening between the GPU kernel, the CPU proxy thread, and the network adapter and so on. And now, one thing to note over here is that our serving, the scale of our serving, the inference, is much smaller. So the scales of tens of GPUs. It's not very large. We're not talking about thousands of GPUs over here. But even at that small scale, low latency collectives are they're very highly desired, but extremely hard to achieve. This is mainly because GPUs and NICs are treated as separate decoupled entities, and we kind of need them to work together to be able to achieve a low latency collectives. Here we're talking about, our goal is to be able to get to collectives in like a couple of microseconds. But that's, we are far from that today. For example, there's no GPU initiated communication. So going to the CPU and going to the NIC, that itself adds a few microseconds right there. CUDA kernel launch itself is like 5 to 7 microseconds right there, and so on. So all of this is, we're talking about like several tens of microseconds, 20, 30 microseconds for doing a simple collective, whereas what we are really looking for is maybe like a couple of microseconds we should be able to do a collective. Theoretically, we can. It's just we don't have a good mechanism of coordinating between GPU and NIC and the software stack to be able to do this. Now, this example was given in the context of Nickel, but these shortcomings are shared by other libraries too, such as MPI. Now, there exist some libraries like NVSHMEM, for example, which have GPU kernel-initiated communication, which can do better. But by and large, this is a problem that exists in most communication libraries. All right. Last section before I close this talk is about the challenge on infrastructure fungibility. So, like I mentioned, generative AI or llamas are not the only models we use. We have recommendation models, and in fact, they are a big part of our infrastructure as well. And they're very different in their behavior. So recommendation models or DLRMs is, for example, the training takes about 100 gigaflops per iteration. In comparison, generative AI is several orders of magnitude larger computational complexity. So the number of GPUs you need, the amount of compute you need is much larger for that. And on the serving side, inference side, there's a big difference in the amount of time and amount of compute required for serving recommendation models and Gen AI models as well. So just to give you a context of here, recommendation models typically use hundreds of GPUs for training. That's the order. Depends on the model, of course. But roughly speaking, hundreds of GPUs for training. Gen AI models use tens of thousands of GPUs for training. Recommendation models can typically be served in a single node with 8 GPUs. Gen AI models require distributed inference with tens of GPUs, multiple nodes connected together to be able to serve. Now, what this means from the from the infrastructure perspective is that we come up with this like bizarre curve that you're seeing on the right-hand side with respect to the requirements that each of these models place. Some models are very compute intensive, some models are memory bandwidth intensive, some are memory capacity intensive, network bandwidth, network latency, and so on. So it creates this huge wiggly thing with all these requirements that are there. And these are two disparate requirements for us to kind of consolidate into a single supercomputer. You could build a single supercomputer that is that kind of optimizes on all these dimensions, but honestly, that might be wasteful from a cost perspective, because building a 10,000 GPU cluster might not be useful for inference at all, even for Gen AI inference. It's just we've never used that many GPUs all connected together. So we have to kind of think about trading specialization of platforms with the cost of maintainability and fungibility. Now, we can't go to the other extreme either. We can't say that we will have independent SKUs for each model. Now, these are just classifications of models. We have many subcategories of this model, many classes of these subclasses of these models. We can't create a separate SKU for each model. That's just not practical from a maintainability perspective, and of course, just from a cost of building so many SKUs perspective. So this is a very strong trade-off that we need to keep an eye on for our systems. We have to be able to get the best performance for our models, but the cost of doing that cannot be significantly high as well either. All right, I have about 9 minutes left, so let me quickly close this. Let me say a few takeaways for people. One is scale changes everything. I've spent a lot of my career talking about improving raw performance, so building out systems that do great from a raw per GPU performance perspective. Often, at least at Meta, performance, and I would assume at most hyperscalers, performance is raw performance is almost never the core problem. Performance is often constrained by many different things, like power, physical layout of the data centers, system reliability, and other physical constraints. These are all, so think of it as I'm trying to optimize performance in a very constrained environment. That's really the problem we're trying to solve, not just the raw performance that I can achieve in a lab. That's one of the big things over here. Second, training and serving are both important, but they are very different problems, especially for the network and for the overall system design as well. Training focuses on scale, a lot of data. Serving focuses on the latency of response. So the kind of optimizations that we need to do for training are very different from the kind of optimizations that we need to do for serving or inference. But these are very tightly coupled problems. So you can't train a giant model that cannot be served easily. Otherwise, what's the point of that model? You can't use it. So we have to kind of think of these two, even though they're very different problems, we have to think of both of them. We should be able to solve both of them in order to be able to deploy a real system. Otherwise, it's not very useful to do that. And last, hardware fungibility is extremely important in production. Specialized SKUs are okay sometimes, but we can't willy-nilly create a specialized SKU. The bar for creating one should be quite high. Okay, that's all I have. Let me spend a minute to talk about the opportunities to work together over here. Meta is a very open culture. We collaborate a lot with a lot of people, academic environments, other industries, and so on. We have, of course, this full-time opportunities in communication libraries. We're looking for experts in comps libraries in general, MPI, Nickel, OFI, UCX, SHMEM, whatever, RDMA, generally in RDMA as well. And other areas of hardware software co-design too. At least my team, it's a research arm. It's not a production team per se. So, but we work very closely with production teams. So if we have an opportunity to build production systems, but also do research hand in hand. So I think it's a good place to work at. Internship opportunity exists for 2025. Sabbatical opportunities exist, and of course, if you're just looking to collaborate, to work on a cool research idea and publish some papers, we are fully open to that as well. Okay, I will pause here. Let me stop sharing.
Thank you, Pavan. Very much appreciated. We have just a couple of minutes if there's some questions for Pavan. Raghu.
Yeah, thank you for the talk, Pavan. That was quite comprehensive. Question, like a broader question about how you, both as a team and as a company, kind of think about which parts of the stack to optimize for when you have these conflicting requirements from DLRM and you talked about the GenAI example, right? Like, it's one thing to build discrete systems or discrete clusters for those use cases, but there's like a lowest common denominator in a lot of the building blocks in the software stack. And it's harder to make a case for building separate stacks for them in some ways, right? Like, how do you think about investing in software optimizations across the stack for these different use cases?
Oh, between ranking and GenAI, it's not an we don't have an option to pick and choose. We do have an option on other models. There are some models obviously that are more critical than others. So optimizations for one would be prioritized. Of course, we have many such examples, but your question was more with respect to GenAI versus ranking. That is not something we can pick and choose. It is, it's asking about current business versus future business. We we obviously can't prioritize those two. Oftentimes we are like I said, our big bottleneck is the power. So oftentimes we are not capex restricted. So many times we can just or we can hire a separate team. For example, if you need two separate set of optimizations in this case. One example is we have a team of folks, a Tiger team of folks dedicated on optimizing comms for GenAI. Now, that is because there are separate set of optimizations that are not relevant or useful for recommendation models. So we went ahead and hired a separate team of optimizations, just developing a separate software stack for our GenAI optimizations. And we would eventually merge those back in, but for the time being, we just went ahead and do that when there are these sort of conflicting requirements. That's from a software stack perspective. From a hardware perspective, it becomes a little more problematic situation. Generally, both GenAI and recommendation models are so important that, for example, training for those, we try to build a system that is usable by both. We cannot make a trade-off over there. We cannot say that this only works for GenAI, doesn't work for recommendation models. I don't know if that answered your question. It's
It did,
bit
yeah.
of a hard question.
It did.
Yeah.
No, it did.
Yeah.
Thank you.
Cool. We have a question on the chat. This is from Seth. Why is power such a big constraint? Is it just the environmental initiative, or do you run into other constraints such as heat?
It's mostly the environmental constraints. It's the same problem for other hyperscalers too. Meta is a little bit more extreme in that case, that we want to have 100% renewable energy neutral, which means any power we take has to be put back into the energy power grid through either wind, solar, or hydro, whatever other sources that we can come. Other hyperscalers have a little more relaxed view on this. Like for example, Amazon recently purchased a data center that's powered by a nuclear power plant for up to 2.5 gigawatts. That's not renewable energy, but it's still clean energy, still carbon neutral energy, which is not bad, which is still a great initiative. But we are a little more restrictive because we are currently saying that it only has to be 100% renewable energy only, fully sustainable. So it is growing, but imagine this, right? You can't just put a data center and pull more power into it. You also need to build a solar farm or a wind farm to put in that power. And so it takes a lot of time to build all of that. That's really where the restriction is coming from.
Great, thank you. We have just a couple of seconds left if there's another question. Okay, well, thank you very much. That was a very good talk. I appreciated it.